Okay, I said I was going to do these in groups of 10, but 29 through 33 are a block. And so I want to talk about these together because they all involve the same basic equation. So what's happening is you're starting with PCl5 and it is decomposing into PCl3 and Cl2. And PCl5 decomposes into PCl3 and Cl2 according to the equation below. A pure sample of PCl5 is placed in a rigid evacuated 1 liter container. The initial pressure is 1 atmosphere. The temperature is held constant until PCl5 reaches equilibrium with its decomposition products. The figures below show the initial conditions of the initial and equilibrium. So basically, I'm going to toggle down a little bit. And they're talking about pressure, so I'm going to use the KP. Initially, this is 1 atmosphere, and this is none, and this is none, and then they don't say much about the change, but they say the equilibrium is that, okay, so let's just say this is negative x, because this has to go down, and this is positive x, and this is positive x, and then this is 1.00 minus x, and this is x, and this is x, and then it says the initial pressure, the sum of all of the initial pressures, the total pressure is 1 atmosphere. And then it says the final, or the equilibrium pressure, see it says figure 2 equilibrium, the total pressure of these is 1.4 atmospheres. And I actually would like to solve that problem because it just jumps out at me. I love equilibriums with pressure because the math is so easy. So Dalton's law of pressure says that the sum of the pressures is equal to the total pressure is equal to the sum of the individual pressures. So this gas and this gas and this gas has to equal 1.40, and so this x cancels this x, and we get 1.00 plus x equals 1.4, and then without a calculator, we subtract 1 from both sides, and x ends up being 0.4. And so if you look here, this is 0.4. And this is 0.4, and this is 1, sorry, down here, these are 0.4. This is 1 minus 0.4, so this would be 0.6, and it kind of makes sense that 0.6 plus 0.4 plus 0.4 would be 1.4. Now, that's not the question. What is this question asking? If I put my pen down, this question is asking, come on. Oh, look at this, I'm moving my boxes around. It's not what I want to do. I want to move this whole thing down. Why does the pressure go up? Because there's a decrease in the intermolecular attractions? No. There's an increase in the strength of, and I think there's more gas molecules because 1 mole of gas is here and 2 moles of gas is here. And when 1 mole turns into 2 moles, an increase in the number of molecules increases the frequency of collisions with the walls of the container, and that's the reason the pressure goes up. Intermolecular forces tend to do with phase changes, and this is not a phase change. And this is 29, I'm not on this page, and the answer is C, so I was right. Let's figure out what I'm doing here. Now, picking this up, as the reaction progresses towards equilibrium, the rate of the forward reaction increases until it is the same as the reverse reaction at equilibrium. I think that's true. It stays constant before and after equilibrium is reached. No, it's constant speed after equilibrium is reached, not below. It decreases to become a constant non-zero rate equilibrium. No, because the forward reaction, in the beginning, the forward reaction is going faster than the backward reaction, but then at equilibrium, because you have a lot more of the stuff on the left and the little stuff on the right. So this one is faster first, and then this one is slower at first, but this one starts to slow down and this one starts to speed up until they're the same. And the reaction rates never go to 0. It looks like nothing's happening because the forward reaction and the backward reaction, but if 14 molecules per second are going this way, that means 14 molecules per second are going this way, and the rates are the same. And so what happens is the forward reaction I don't know if it is A. I don't think the forward reaction is fast at first, but then it starts to slow down. So the forward reaction in the beginning is really fast and the backward reaction has nothing. And then, no, it's not this. It isn't constant before equilibrium is reached. It's only constant after equilibrium is reached, so that's wrong. I think this is wrong. I think the forward reaction decreases. It's really fast in the beginning because you have no product at the very beginning. So it's fast at the beginning, it's non-existent, back one's non-existent. And then this one, then the next time this is a little slower and this is a little faster, and then a little slower, a little faster, a little slower, sorry, a little faster until they're the same. So the reaction, for every reaction decreases to become a constant non-zero rate at equilibrium. I think the answer is C, and I think I did a pretty crappy job explaining that, but that is the answer. Okay, let me just try to explain that one more time. In the beginning, you have 1 atmosphere of this and none of this. Remember, the rate of reaction is based on the concentration of the reactant. So in the beginning, the instant it starts, this reaction is very fast and the backward reaction is non-existent because you don't have any of this to make the backward reaction. After a couple minutes, this is slowing down a little bit. This is speeding up a little bit. You're still not at equilibrium because they're not the same. Couple minutes, days, whatever the time is, this is slowing up, this is speeding up, you're still not at equilibrium, and eventually get to a point where those arrows are the same length, and that's when you're at equilibrium. All right, if decomposition were to go to completion, meaning not equilibrium, if this were to go to completion, the total pressure would be 1 mole of gas would turn to 2 moles of gas. If it went to completion, not equilibrium, but completion, 1 mole of PCl would disappear and become 0. And these 0 moles in the beginning would go to 1s, and 1 plus 1 is 2. And so if it went to completion, not equilibrium, I believe that the pressure in the container would be 2. Which of the following is true about Kp for the reaction? Well, I actually know these. Kp is the pressure of the PCl3 times the pressure of the Cl2 over the pressure of the PCl5. And we figured out that this was 0.4 and this was 0.4 and this was 0.8. And so this is 0.16, sorry, 4 times 4 is 16, and then I gotta go to 0.16 over 0.8. If I multiply this by, let's say 100, so it makes sense, 16 over 80, you can see obviously 16 over 80 Kp is less than 1. And so I think the answer is A. Oh, that isn't. I said Kp is less than 1, and then I circled Kp is greater than 1. I don't think the answer is A. I think the answer is B because I'm a moron. All right, we already talked about this one. I just want to hit it again. You have the system at equilibrium, and you inject some of this in, and it's going to force, because now we have more of this one to speed up for an instant, and then this one doesn't change, but then this starts to slow down, and then this starts to speed up, and they hit equilibrium again. But what you need to understand is you put more in there, and it's going to come to equilibrium, but you're going to, because you have more molecules, when you injected the Cl2 in there, you now injected more molecules, and when it comes back to equilibrium, instead of having like 8 and 8 every second, it might be 10 and 10 every second, because more molecules means more rate, but at equilibrium. Now, this is what I want you to see on this problem. Okay, I gotta quit doing that. I just gotta do this. The reason why the answer is B is it's at equilibrium. The instant you inject the chlorine, you get this huge jump in the reverse rate. Okay, so at first, when you put in there, the reverse rate really speeds up and the backward rate doesn't change. But then this one starts to slow down and this one starts to catch up. and this one starts to slow down, and eventually this one catches up. So this is at equilibrium, this is at equilibrium. This is the huge initial jump, but then it starts to slow down and it goes back to equilibrium. But the new equilibrium, the rate per second, you know, instead of being 8 molecules per second, it might be 10 molecules per second now, because you put more stuff in there. Now, if you, this answer C, I kind of like, this would be the answer if, sorry, this would be the answer if you, if instead of adding Cl2, you could do something like you removed, let's say you removed PCl5. But what happens is, if you look at the equation, you remove some PCl5, the system says, hey, I don't like that you took the PCl5, I want it back. So this one does speed up to try to get it back, and then again, it's equilibrium, speeds up for an instant, but then that one has to slow down and this one has to catch up. But now you took some PCl5 out, so there's less molecules in the container, and it comes back to equilibrium, but the rate is a little bit lower per second than it was before. So you get the huge jump when you take some out, and then the backward reaction slows down and it comes back to equilibrium. But because you remove some PCl5, it's just a little bit lower than it was before. Okay, this is a really tough problem. The elements K and Cl react directly to form the compound KCl according to the equation below. Refer to the information in the table below. Okay, so here's what it's saying. In order to get this reaction to go, the first thing that happens is that potassium metal in the solid state has to become potassium ion in the gas state. And then, because KCl is an ionic compound, +1, -1, then you have to take the potassium ion in the gas state, sorry, the potassium atom, and turn it into a potassium ion by removing an electron. And then Cl2 is this, remember we talked about this shared pair, and in order to get K1K to hook up with 1Cl, you have to break this apart. So you're taking a Cl molecule and converting it over back to 2 chlorine atoms. And then that chlorine atom has to accept an electron to become a chlorine ion, and then opposites attract, and the two gases hit, and they're so attractive that they come together and they go back to the solid. And you can see that if you added and subtracted the things on both sides, K solid plus 1/2 Cl2 gas goes to KCl solid. Now, how much heat is absorbed or released when not 1/2 mole of chlorine gas is formed, but not 1/2 mole, but 10 times less? So I mean, the equation right now says that when you have 1 mole of K and 0.5 moles of Cl2, you get 1 mole of KCl, and the delta H of that reaction is negative 437 kilojoules per mole. And the question is, if this was not 5, but it was 0.05, remember, you don't get a calculator, and 0.05 is 10 times smaller than 0.5. And so does it make sense that the heat of a reaction would be 0.437 divided by 10? And so the best answer is B. 43.7 kilojoules is released. It's still negative. It's just that you're not using 1/2 mole of chlorine, you're using 0.05 moles, so 5, not 5/10, but 5/100, and so it's 10 times, this is 10 times smaller, and so the answer is 10 times smaller. 35. What remains in the reaction vessel after equal masses of KCl and Cl2 have been reacted until either one or both of the reactants have been consumed? Now this is a crazy, not crazy, But this is a limiting reactant problem. So this is what I would do. Here's your equation. So you have K plus 1/2 Cl2 goes to KCl. Now you have equal masses. So I'm going to look at the chart, and potassium is like 39.10 grams per mole. And chlorine is like 35.45 grams per mole. So if you doubled it and then took half of it, so this is 35. So basically for this reaction, 39 grams of this would react, if you had 1 mole, 39 grams of this would be 1 mole of that. Reacts with 35.45 grams of that to make 1 mole of this. So the question is, if you had equal masses, so let's pretend, so what I'm thinking is, because in this equation, this is smaller, if you had equal masses, like you put in 35 and 35, like the equal, maybe that's a bad way to do it. Man, I need to think about, how did I do this when I did it? Okay, so let me look at the answer. I'm cheating. 35. They're very similar, and so the answer is C. What remains in the reaction vessel after? The answer is C. So obviously, this means that the limiting reactant is potassium. So the limiting reactant is potassium because all the potassium is gone. Now, how can I explain that the limiting reactant is potassium? I guess I would say this. If we did equal masses, let me just pick 10. 10. If I did this, 10 divided by 39 grams per mole, and 10 divided by 35.45 grams per mole. Remember, I already took care of the fact that this is a half and this is a 2 by taking, 35.45 times 2 is 35.45 times 2 divided by 2. It's still 35.45. So if I do this in my head, obviously 10 divided by 39 is a smaller number. So this is a smaller number than this. And so this is the limiting reactant. So at the end, this will be completely consumed. You will have some KCl, you'll have a lot of KCl because this reacted with this making KCl, but this runs out first, so you're going to have a little bit of chlorine left over, and that's why the answer is C, KCl and Cl2. And I did that a really bad way, but you don't get a calculator, so you got to understand that the molar mass of this is bigger than the molar mass of this, as written. But if you had equal masses, the way you convert grams to moles is you divide by the molar mass. And so if you divide by a bigger number, you actually end up with the smallest number of moles. And then this is 1 to 1, this is 1 to 1 after I do that weird thing where I take half of 2. And so that has to be the answer. That's kind of a crazy way to explain it. Oh, this is one of my favorite problems. Which of the values of delta H for a process in the table are less than 0? Under means they're exothermic reactions. Okay, this is endothermic. Here's how you know this. To go from a solid to a gas, remember when I draw those pictures? Solid, liquid, gas. To go from solid to a gas, you have to put energy in to get it. So this is endothermic, okay? This is endothermic. One of the things I was trying to tell you is you always have to put energy into an atom to get an electron away, because potassium has 19 protons in the nucleus and 19 electrons in the cloud, and opposites are attracted. And yeah, it's easier to get an electron away from potassium, but it's still have to put some energy in to make that happen. So that's endothermic. This is incredibly endothermic. Why do you always find chlorine clumped in nature as clumps of 2 rather than alone? Because A chlorine atom has 7 valence electrons, and every element wants 8. And so what happens is these two approach each other, and they decide to share these electrons in the region of overlap, and now they both have 8 electrons in their valence shell. And to get something that's really stable to separate and to become non-stable is endothermic. Now, this is exothermic. Here's why. Chlorine has 7 valence electrons. When it gets an electron and turns into a chloride atom, it is excited. It's more stable to have 8 electrons in its valence shell than 7. And so when a chlorine atom picks up an electron, it becomes more stable. So it has to exit. And obviously, looking at my thing, opposites attract and 2 gases come together to become a solid. That's incredibly exothermic. And so the only 2 that are exothermic processes in my mind are Y and Z. And I better check that for 36. Yep. Okay. 37, last one. It is observed that the reaction producing KCl from its elements essentially goes to completion. Which of the following is a true statement about the thermodynamic favorability? Now, you have to look up here. They told you that delta H was negative. That's good. If you look at the process, though, delta H is not positive. It's negative. Why? Because half a mole of a gas is turning into 1 mole of solid. It's becoming more ordered. But because it essentially goes to completion, we know that delta G is probably negative. So what's driving this reaction is that this must be bigger than this, because remember, gators are hell without tartar sauce. And so in order for delta G to be negative, delta H is negative. But a negative times a negative is a positive, but this must be the overpowering term. So I would say the reaction is favorable and driven by the enthalpy change could be true. It's not driven, it's not unfavorable because it goes to completion. It is driven by both enthalpy and entropy, but entropy is warring with enthalpy because spontaneous reactions tend to occur. This is spontaneous reaction. This reaction just happens. When you put potassium and chlorine gas together, it spontaneously makes potassium chloride because that's why there's so many more compounds than elements. It's more stable for them to be a compound than element. And the reaction is unfavorable. That's not true because this reaction is spontaneous. So it has to be this, and it's driven by enthalpy because in order for it to be favorable, delta G has to be negative. What does the answer key say? It predicts correctly that the sign of the free energy change would be negative or thermodynamically favor since it goes to completion and driven by an enthalpy change since the overall reaction listed is exothermic. The reaction is not driven an entropy change because the entropy of the system decreases, not increases. So yeah, basically, that's crazy. Now, this is a Hess's law. So if you look at this, so many. I want to go Cl2 on the left-hand side. Cl2, that's this one. Okay, I need this to be here. And I need 2 Cl to be on the right-hand side. 2, so I'm going to have to double this. So what happens is I'm going to take reaction 1, Cl2, sorry. Cl2 goes to 2Cl, and that's X because I haven't done anything to this. And then this reaction I'm going to double, and then 2Cl plus 2 electrons goes to 2Cl minus, and then this would be 2Y. And when I add these together, this cancels this, and I get Cl2 plus 2 electrons goes to 2Cl minus, and delta H would be X plus 2Y, and I hope that solution is there, C. And I hope that 38 answer is C. And it is. And then 39. Oh, this is interesting. I like this problem. Okay, so we have volatile means it enters the vapor phase. One of the things you're supposed to know is that two gases at the same temperature. So you have gas 1 and gas 2. And if they're at the same temperature, they have the same kinetic energy. So the kinetic energy of 1 equals the kinetic energy of 2. Sorry, kinetic energy of 2. But kinetic energy is 1/2 mv squared. So the kinetic energy of gas 1 is 1/2 the mass of gas 1. This is 1/2 mv2 squared, and then I'm going to double both sides, and I get m1 v1 squared equals m2 v2 squared. And getting the m's on one side and the v's on the other, you get Graham's law of diffusion, which is the ratio of the velocities are equal to the inverse square roots of the molar masses. Notice they switch positions. The square root is coming from the fact that you have to take, to get v alone, you have to square it. Why they flip is that if you get the v's on one side, you divide both sides by m1, and then v2, v2, and what you'll notice is the 1 is on the top here, but it ends up being on the bottom down there. And the reason is because the gases that are the lightest, as the molar mass goes down, their velocity goes up, so they're inversely proportional. What this question's getting at is that you have two gases moving towards each other, and which pair of gases would the white ring, which indicates the gases, have run into each other? Where would the white ring be the closest to the center? And it would be the closest to the center when the velocities are the same, because they meet in the middle if the velocities are the same. If the velocities aren't the same, like let's say this thing moves a lot faster than this, they're going to meet over here. And so in order for the velocities to be the same, the molar masses would have to be really close. So just very quickly, round to the nearest whole number. Hydrogen is essentially 1. This is 35.5, let's say. So this is 36.5. And this is 12 plus 5 plus 14. So 26. So this is 29. No. Okay, 6, 9, 10. Oh, I'm losing it. I'm tired. 12 plus 14 plus 5. So 12 and 14 is 26. So this is 29. And then this would be 36.5. And then 14 plus 3 is approximately 17. And this would be 1 plus, and bromine is 79.9. So 80. This would be 81. And then this is the same gases up here, 29. And then this is 81. And this is 17. So the question is, which pair has the closest molar mass? It's A, 36.5 and 29 is the closest. 36.5 and 17, 81 and 29, 81 and 17. The one where the molar masses are the closest, so they meet in the middle because they have rough, or the closest to the middle. So 39, the answer is A. This option is correct. It demonstrates the understanding that gases with similar molar masses at the same temperature will travel average speed. Okay, this is, what am I doing wrong here? Hydrogen is 12, and carbon is 12, and nitrogen is 14, and 12 and 14 is 26, and 26 and 5 is 31. I'm an idiot. I can't even add. These are 31. I'm looking at the key going, where the heck did I get that 29? Sorry about that. I calculated the molar masses wrong. 40, last one. Silicon crystals are semiconductors. That means they kind of conduct like metals, but they're kind of insulators. Which of the following is the correct reason for the increase in the conductivity of Si crystals when a small fraction of Si atoms are replaced with those from a different element? So this is what you got to know about this problem. If you want something to conduct electricity better, you have to add more electrons. I think it's called doping. If you want a semiconductor to conduct electricity less, you have to remove electrons. Now, if you look on here, silicon has 14 electrons. Okay, so then it talks about potassium, or sorry, not potassium, phosphorus and germanium. And phosphorus has 15 electrons. And germanium has 32 electrons, but it's not that complicated. It's not that simple. We have to talk valence electrons because those are the electrons. So phosphorus, okay, silicon has 4 valence electrons, and phosphorus has 5 valence electrons, and germanium has 4 valence electrons. So if you want this to increase the conductivity, you need to dope it with something that has more valence electrons. And so what would you replace with? P atoms introduce additional mobile electrons. That's interesting because that's what a metallic bond is. I'm pretty sure that A is the answer. You don't have mobile positive charges. Positive charges don't move, negative charges move. GE atoms have more electrons than SI atoms. That's true, but all bonding occurs in the valence shell, and so it doesn't matter. They have the same number of valence electrons, and germanium atoms obviously are not smaller than silicon atoms. So I think the only answer that makes sense, if you understand metallic bonding, is on 40 is A. This option is correct. It recognizes that phosphorus atoms contain 1 additional valence electrons over silicon atoms that make up the bulk of the material, and these additional mobile charges will increase the conductivity of the metal. So this is a question about metallic bonding and this idea of the electron C model for metallic bonding.